Well, welcome everyone to the final presentation of the day one at Black Hat. I hope everyone was able to make it through the day, keeping your eyes open and not falling asleep after the parties of last night. We just wanted to introduce ourselves really quickly since we're new presenters here at Black Hat. My name is Ben Feinstein. My background is primarily in security, software engineering. I've been working in that area since about 2000. Working on products such as next generation firewalls, messaging security, IDS systems, and now I'm a researcher at SecureWorks. To my right is Daniel Peck. He's a proud graduate of the Georgia Institute of Technology. He's the resident reverse engineer on our research team, and he's kind of a jack of all trades other than being an IDA Pro jockey. And we got a lot of questions the past couple days. Who is SecureWorks? Some people had not heard of us. We're primarily a managed services provider. We also have a professional services group. We specialize in network IPS and IDS, vulnerability assessment, log analysis and monitoring, and firewall monitoring. So our talk today is about malicious JavaScript. And we may not need to ask this question, why should you care, after several of the talks today, but we're going to answer it anyway. JavaScript is now used today by a lot of Trojan downloaders. As you've seen today, it can be used in browser exploitation. Some new attacks involve information leakage. They'll grab your browser history. They can grab cookies using scripting on the browser. And there was an interesting talk today regarding using scripting on the browser as an endpoint into the network and actually being able to scan and attack internal sites on your intranet through the browser. Primarily, we're looking at evasion and obfuscation techniques that attackers are using with JavaScript to bypass security technologies, such as IPS or IDS devices or host firewalls. So just a little bit of the history of JavaScript. I'm sure some of y'all are familiar. Netscape came up with this great concept back in the 90s. And the idea was basically to allow dynamic interpretation of a scripting language in the browser. Some of this was animated cursors. Some of this was just more rich interaction with the browser. There's been a various number of incantations of JavaScript. There was the original Netscape JavaScript. Microsoft came out with JScript as that gained popularity, and now it's been standardized as EMCA script. But we'll just use the term JavaScript interchangeably to refer to this technology. And contrary to popular belief, the document object is not really a part of the standardized JavaScript. A lot of the more advanced techniques, as you saw in the talk in this room just before, using AJAX kind of communications, those are really browser extensions to the core JavaScript language. And why this creates such a problem for the security world is really, this is blurring the line once again between data and code. We're going to talk more about what we mean when we say that, but essentially the data is interpreted code. It's hitting your browser. It's being interpreted. It's changing things in your environment. However, to a security device in line, it's typically inspected as if it was just simply data. So
feature and functionality bloat. We've all seen JavaScript expand quite a bit in the last couple of years. Things have expanded, websites have become more dynamic. You have sites like YouTube, MySpace, etc., with just JavaScript everywhere. So the biggest thing about this is AJAX has really led to a lot of the bloat. People discovered that they could be more dynamic, get more interaction, not have to hit that refresh button constantly. And users really like that. It adds a lot more seamless and lets it be a real web application instead of just a web page. The XML HTTP request was the first kind of incarnation of this where things came about, got going with it. It's used extensively now. You see it in Gmail, all the Google apps. More websites are out there every day. But the problem with it is more features, more attack surface. And not only that, is that most of the time vulnerabilities occur at the edges of functionality. Things that the initial author might not have fully tested or added at the last minute. And this is something that we really see a lot of in JavaScript, is that originally it wasn't meant to do all this. So Web 2.0, It's an amazing thing and is really on the forefront of technology. Everything is Web 2.0 now. Anything that takes in client input, puts it up again, interacts with the user. But you can't really use the web without it in a lot of ways today. These things, if you turn off JavaScript with your NoScript kind of extensions, most of your websites aren't going to work. YouTube's going to complain. Any number of other websites are going to complain. And there's not really too much you can do about it except for run them. Because turning off the script, while it might be a valid thing for those of us in this room to do, it's not something that most users are comfortable with because it breaks their experience. And they're using these websites for the experience. Back one, actually. So it's advice to your typical website designer, developer. A lot of your website designers, they didn't exactly have the best training in programming. Not to any fault of their own, but most examples online that you find at the JavaScript libraries, things aren't secure. You see cross-site scripting everywhere. You see file inclusions. All this kind of stuff is just all over. And that's what happens when you have a technology that's just exploded in growth. It didn't have a lot of time to mature. So is it really that dangerous? Well, yeah, it's becoming more dangerous all the time. We saw some things in the month of browser bugs last year. Number 25 was the native function iterator, which was basically a pretty simple thing where if you run an iteration, a for loop, over a native JavaScript function, get a crash, and you can get remote code, which is kind of the goal of these things. Another thing, we saw a good example of other ways that JavaScript is used in malicious efforts was month of browser bugs number 8, which went through tons and tons of iterations, 65,000 times. You wouldn't want to download a web page that large, but you could download an 8-line JavaScript that'll write all that out to the page after it's on the client. You're getting a lot speedier, a lot less time, a lot less intensive, and it's all happening on the client. Some more advancements we're seeing is the GNU Citizen Group has put out their attack API, which I'll be honest, I haven't had a whole lot of experience with, but from what I've seen, it's very extensive and really gives you a great framework for exploiting JavaScript and various other kinds of technologies on the web. So this is only going to become a bigger and bigger problem. Other things we've seen, I know it was talked about today in Mr. Kaminsky's talk about using the browser to gain access to internal networks and sending stuff back through Flash and other mechanisms. And we've seen that last year also with the guys at SPY doing the pen test from outside the network, being able to run Nmap basically through JavaScript, and the same with Jeremiah Grossman. A lot of these ideas came about at the same time. It's also used extensively in cross-site scripting, like I said. Everyone should be familiar with this. It's the seemingly ubiquitous vulnerability. New products are coming out with more and more cross-site scripting vulnerabilities than the security community can find. You can't keep up. And they're everywhere, and they're just getting more and more dangerous. What used to be just a simple trick that you could make an alert pop up and say, hello world or something, or my first exploit, now you can really start to do some damage with some of this JavaScript, especially when you're sticking Ajax into it. Persistent cross-site scripting where you're having stuff that's going to stay there and keep on exploiting people. And I know Billy just got done doing a talk involving a lot of those things, and it's only getting worse. You're seeing a lot more of it at conferences like this. Another thing recently, to give an example, was the eBay seller ratings. And it was a pretty simple little cross-site scripting hack that allowed the seller to show that he was a power seller, had thousands of positive ratings, positive transactions. And that might not seem like a big deal to you and me, again, but to grandma or mom, it might be an issue. They're going to trust somebody a lot more with this power seller rating that eBay has ranked them than with no feedback or negative feedback. You can get in a lot of traps and start losing some real currency and hard work. And also the numerous address bar spoofing that we see in phishing things. There's been so many vulnerabilities that involve being able to do that it would waste a lot of time to count them all off. But they're very common and very easy to do. Some other postmortems. The Super Bowl 40 Dolphin Stadium website got hacked, had a Trojan downloader, keylogger. It was a pretty simple iframe injection. The server was compromised, had an iframe on the front page, which downloaded some malicious JavaScript, and then attempted to run a couple of exploits against Microsoft products that had already been patched, but due to the patch consistency of most users, was still fairly effective, though there were some problems in the exploit, and it wasn't as successful as it could have been given the circumstances. Another thing, speaking of blurring the line between data and code, is we've seen that QuickTime movies can have JavaScript embedded in them. You don't know what's data and what's code anymore, because you're downloading these things and running it, and what you would originally think is just a simple media file of, a video that your aunt sent you or something, is now can be malicious code. Same with Shockwave Flash. We've now seen the inner platform effect, because we have Flash running on the browser, running on the OS, and you got a network stack all the way down. That's going to cause a lot of problems in the future. And we're starting to see it pop up more now as people start to experiment with the network stack in Flash, because not a lot's been done there. It's a very ripe area for exploitation, and we're going to see it happen more and more. Earlier in the year, we saw the Adobe PDF cross-site scripting, which was trivial to exploit and affected everything. Because who doesn't use PDFs or Adobe PDF Reader? It's a near ubiquitous piece of software and installed everywhere. So those are just a few examples of what's really going on in the world these days. So now we're going to move into talking about some of the ways these are actually done in the real world, some of the evasion and obfuscation techniques employed.
Just to kind of review some of these techniques that we see in the wild and that are frequently used, one of the most simple evasion and obfuscation techniques is basically, we call it white space randomization or comment randomization. And the reason this is so effective is because a lot of security appliances are looking at a byte stream on the wire and are trying to make decisions about the intention of that traffic from just simply looking at that on-the-wire network footprint. Well, you can imagine a JavaScript says, simply prints out the message, hello world. Well, you could add random comments throughout that script. You could use white space between the operators in that script, and that's going to completely change the byte stream on the wire that signature-based network appliances may be looking for. Another simple technique is string encoding or unencoding. This is not just specific to JavaScript, obviously, but in a lot of these malicious JavaScripts, you will see frequently use of encoded characters, Unicode, unusual Unicode encodings. Also, you frequently see the use of the character function, or I believe it's CHR function, to pass ASCII values and then have them converted dynamically in the script into their ASCII character equivalents. And the examples we put up really just barely touch the surface of some of these encodings. Some recent vulnerabilities have used wide Unicode or extended Unicode code pages, and there's actually ways to encode the ASCII character set in a whole variety of ways. And with the internationalization of all the software, there's much Unicode support, and a lot of security mechanisms don't handle it quite right. So you can get your attacks through these devices by using unusual Unicode encodings that are happily decoded on the end application or the end server. Another very simple technique is string splitting. As you've seen here, if you have a string that you need in your script, here we had lots of detections fail. It could have been, some XML object that you're trying to instantiate. Well, you don't necessarily want to put that string directly into your script because there may be security devices in line that are looking for the instantiation of some XML class or a particular exploit code. So you can simply split that content payload up any way you want, and have that string concatenated throughout the script dynamically during interpretation or runtime. And naive approach to content filtering in line is going to miss these kind of things because there's literally infinite ways that you can string concatenate your desired payload together. A few other obfuscation techniques to look at. Integer obfuscation. If you have a particular number that you need to use in your exploit, you would be rather naive just to have that number defined in the script. There may be some security mechanisms that are looking for that particular content. Well, just like we showed with strings before, there's infinite ways you can add and subtract and multiply and divide and use just basic operations to eventually yield a variable with the integer value that you're looking for. And here, the example is just, here's one way to encode 31337. You could obviously get much more sophisticated using mathematical operators or bit shifting and things of that nature, hex values, that will kind of throw a monkey wrench in the whole inline security device that maybe takes a naive approach to looking at these things. I recommend y'all check out Alexander Sotorov's talk tomorrow on JavaScript heap spray, and or as he terms it, JavaScript feng shui. Basically, the idea there is that your JavaScript, since it's being interpreted dynamically in the browser, all that execution is affecting the heap of the browser, the memory space of that application. So, if you're trying to exploit the browser for whatever purpose, you may spray trampolines or exploit code, or depending on your exploit, across the entire heap of the browser. And then it's kind of like, you're setting someone up for a 1-2 punch. You essentially spray your code, your exploit code, your trampolines, whatever, across the heap, and then you follow up with the exploit and you jump into that memory area. So once again, the dynamic interpretation of this stuff in the browser is really making the security of that application more brittle. And one interesting aspect of JavaScript is it's so dynamic. Variable names, function names, class names can all be redefined as many ways as you like. So just because someone is calling document.write or some normal function, CHR, earlier in a script or in another script that's been included, they may have redefined that function. It may actually be evil hacker's function, yet in that script it's simply CHR or write. And so, one of the power of JavaScript is it's so dynamic and you can redefine everything, but that's also a big weakness from a security perspective, because if you're looking simply at the syntax of that script, you're never quite sure what the real meaning of those variables or functions is, because they could have been redefined at any point prior in that execution. More sophisticated technique we've seen is block randomization. And so you can imagine if you're trying to achieve some end in your script, you can basically wrap it up in a variety of for loops or while loops or do while loops. Sometimes they may actually work out to be essentially a no-op. They don't do anything. They're just simply to fool the analyst or to throw off a security device. But it's much more sophisticated and difficult for a security mechanism to really unwrap those loops and unravel those loops to determine what this script is really doing, short of actually executing it. And that's not always a feasible approach for an on-the-wire kind of prevention device, in that the latency or the resources involved in trying to dynamically interpret these scripts on the wire can be a real challenge. So frequently you see attackers combining all of these techniques together. And that really makes the job of an analyst much more difficult. They may have while loops that, including the while loops, they're doing string encoding in that loop. And maybe they're adding some variables together, string concatenating or integer addition within these loops. And then they're using some Unicode encodings. So short of having some automated tool to do this, it's very difficult for an analyst who has a sample of JavaScript and is trying to either do an incident response or determine what this script is. Is it malicious? Is it benign? It's really challenging unless you had some automated tools to tackle this stuff. And right here, this is just an example of a script, a malicious JavaScript that we were provided from a researcher. And if anyone, by the end of this talk, tells, or by the time we get to the slide that reveals what this is, if you can tell us, raise your hand and I'll buy you a beer. It's very ugly. You could see use of toString. You could see replacements, hex values. It's a real mess. But this is something that was found in the wild, and this is a real example of something we consider highly obfuscated JavaScript. And obviously when you're dealing with something like this, you really want some automated tool. You don't want to sit down and try to figure this out on your own.
So enter Caffeine Monkey, the tool we've developed. Like so many great ideas, it was born at a local bar, sitting around talking about new and current exploit conditions. So we had a few goals in mind for what we wanted this tool to do, to help not only ourselves, but our analysts and the community at large. And that was, we wanted a central database for collection and analysis. We wanted to be able to spider the web, finding new and interesting JavaScript, both benign, malicious, and everything in between. We also wanted a good way to collect these things. Not only a place to hold them, but a good spidering mechanism to hold them there. And we found those, which we'll talk about soon. We also wanted a good mechanism to feed in these collections into various browsers and collect the results. But most importantly, we wanted a safe and lightweight alternative. Because right now there's a lot of different ways that people are going about analyzing these malicious JavaScripts, but they're not really that safe. They go from really benign or really naive approaches, such as wrapping in a text box or text boxed area, where it'll just write the output of the JavaScript function into there, to other really heavyweight approaches, such as having VMware images and running all kinds of behavioral analysis on that. So we wanted to split the difference and be able to have something that the individual analyst could use without a lot of upkeep and trial and doing away with new images all the time and starting over, along with it being safe. So thankfully, we had a lot of great open source software to build on. SpiderMonkey, which is where the name for our tool comes from, it's the JavaScript engine for the Mozilla project. It's a great piece of code. It's gotten very mature because it's been being built in one way or another for the better part of 10 years and more, and rewritten over that time, of course, here and there. But it's a very mature piece of code, very heavyweight. You can do whatever you need to extend it. If you wanted to put JavaScript scripting into one of your applications that you've just written, you could easily do it. Provide your own DOM or anything else for it to script. You could drop SpiderMonkey in line and just deal with it directly through scripting instead of worrying about coding C all the time, which is kind of a good functionality. We also had the Heritrix web crawler from the good people at archive.org, another very mature piece of software. If you need to crawl websites to gather statistics or info, this is a great tool to look at for doing that. It's a lot better than the LWP script you're going to hack up in Perl. It's had a few more years under its belt to really get mature. And the good people at University of Michigan for some of their Perl and PHP scripting to pull out these archive files and easily allow us to analyze them and dissect them in various ways. So we're going to release this open source database and scripting released under GPL v3. SpiderMonkey extensions released under GPL v3 also. Basically, so that's the good news, and we hope that the whole community will take it and run with it from what we've already done. But basically what we did is a lot of wrapping and logging functions in the interpreter. We kind of split the difference between actually stepping through the code in a debugger and just doing behavioral analysis. We've kind of given it sort of a sandbox place where it can run and not have to deal with any crazy errors that it might come about or anything of that nature, but also to allow it to be run very speedily and accurately and log the output for statistical analysis. Here's a demo screen. Here's the Heritrix web crawler. You can see a couple of jobs being worked. We ran more than a few to get our samples to start off with and run some more since these slides have been created. And it's very consistent, very quick, and just provides a great platform. Here's another example screen of this.
Basically, what you're looking at on this screen is in Heritrix, it has the concept of crawler jobs. And so we went in and we defined some crawl jobs of places we thought we'd find some interesting samples. The first major crawl was of MySpace.com. I believe what we're looking at here is the crawl report from our MySpace crawl. And you can see the vast majority of documents, or the vast majority of content that was retrieved was of a MIME type text HTML. There's a lot of JPEGs, a lot of GIFs. But what is interesting is we collected, about 400 or 500 unique JavaScript documents identified by MIME type across that crawler run. And so this is just kind of showing you the kind of graphs that you're going to see when you're running these crawl jobs through the Heritrix administrative front end here. And just to go back one real quick, what you're looking at here then is completed jobs, completed crawl jobs through the Heritrix front end. And I don't know if you could really make it out, but we've got several candidates we had crawled trying to find some interesting things. We'll talk about those runs a little bit later. But I know you all want to see the output of this tool we're talking about.
So here's Caffeine Monkey, and since live demos are destined to fail strictly by nature, we've decided to screenshot to the better way to go. So here you can see this particular piece of fairly heavily obfuscated JavaScript that we showed earlier in the presentation. We pasted it in here to the tool, and it's sitting here waiting at the command line to process. Our tool all runs on Linux, should compile on any Unix system, but we tested on Linux, both Red Hat and Debian. So if you're having trouble compiling it, it's probably a problem with your distribution, because if it hits those two, it's covering most of the bases. But anyway, it's sitting there waiting. So we get a lot of output. It's very, very verbose at this point, because we just wanted to throw everything it was seeing out at us. That can be tuned down in the future potentially, but for right now it spits out lots of log files. As you can see here, this JavaScript is starting off by building a string up through string concatenation. Every time you see a new string, that's a new concatenation. And you're seeing what it's become. And you can see here it's building up a document write, see what it's putting in. And as it goes, you can really run some analysis and see what's happening here. This is building up something to write into the web page, and it's going to be something malicious, potentially. Here we see it continue some more. We've skipped quite a few lines here because there's no sense in looking at the same lines over and over. So you see the new string up at the top. It's pretty much the complete new string that's being done. It's after quite a few. And then you see a val that's being called, and the parameter, or the document write, is the parameter being passed into the eval function. So here we easily see what's actually being evaled, what might just be dummy code to throw the analyst off, or anything else, because you're actually hooked in to the trace of what would be happening, or what is happening. You see again, it makes some new strings because it's got a couple of pluses in there, the string that is passed into eval, and then it does a document write. And here you can see it adds a source of another JavaScript. And we'll tell you about that later. But this is the final result of that big paragraph of obfuscated code, is it's calling eval on this. Turns out this source downloads another JavaScript. It's another layer of indirection that tends to be used in these attacks. And it might bounce from server to server to server, but it's all over. At this point, it's been injected, and the browser is going to do whatever it says. You can't stop it at this point. Turns out what this particular one did was keep getting an ad, kind of a spyware, adware kind of thing injected into the page, and it was an ad for a Spanish-speaking adult friend finder kind of site. And as we'll see, a lot of ad servers and malicious software use the same. They have a very similar fingerprint and a very similar methodology in the way they're going about things, which we'll talk about some more later. So to address the pitfalls in the current technology while we did this, there's been some other great projects that we've built on or heard about through the grapevine. And this sort of monkey technology has been going on for a little while. The MS Strider project was kind of the first honey monkey project that I really heard about anyway. There might have been some other things before, but they had some really great results. They scoured the web looking for O-Day exploits. There's not a lot of info on the project, but from what I hear, they've had very successful results and patched a lot of bugs and vulnerabilities in Internet Explorer and other tools due to that. Other one, MITRE has a Honey client that they're using, Capture, Honey C. They're all fairly similar, written by different groups for different purposes, but kind of have the same functionality in the end. In general, these tend to be very heavyweight and resource intensive, whether running VMwares or starting up numerous different browsers and running through all the different versions. And that tells you a lot. It tells you a whole lot, because if you're running it in the browser, you're going to see. But at the same time, with simple behavioral analysis, you're going to be bypassed by some other things. Say if the malicious code is date sensitive. If you run it on Tuesday, are you going to have the same functionality as on Wednesday? So then you get into a lot bigger bloat of what would actually be happening, because you're going to have to actually change the system clock, and you can't do that for every conceivable thing. So you really have to go at a deeper level to get the full understanding of what's going on. Now that technique's not used a lot, admittedly, but it could be, and there's other similar techniques that could happen like that also. Also tends to be very high interaction. Some of these techniques also have to be high interaction. Lots of human time, lots of loading up the VMs, lots of running it through. Human analysis, time consuming. Very, very time consuming. I don't know how many of you have ever dealt with malicious JavaScript or malicious code in general trying to figure out what it does. It's very error prone. You take a lot of time running through the various layers of the scripts, the onioning as known. And it's not that safe. As we mentioned earlier, you have your text area wrapper under O-Day conditions. They're probably going to be closing up that text area whenever they're running the script. And then you get stuck doing the same thing. So now we're going to talk about what we found.
So we've talked about the web crawler component, and our idea was to basically try to find some interesting samples of JavaScript content from the wild. And our first target was MySpace. It's a very popular social networking site I'm sure you're all familiar with. For the MySpace run, we captured about 8 gigabytes of data over about 3.5 days. Like I said earlier, we captured about 400 or 500 unique JavaScript documents that were identified by their MIME type. Some other crawler runs that we performed with the hope of finding some interesting samples was serial number or software cracking or whereas sites. Using a little Google hacking, we were able to identify a large collection of .edu servers that had been compromised and were hosting pornography as well as Trojan downloaders. After we discovered that, we decided, well, let's look for some military sites that had been compromised. And being good American citizens, we only looked at other nations' military sites. And basically, we found just some simple Google hacking that you could find a number of compromised .mil, .country code sites that were hosting pornography or Trojan downloaders, things of that nature. And then also the good guys at stopbadware.org have an extensive list of bad news websites, compromised web servers, Trojan downloader hosts, all sorts of places you really want to avoid. But it's a great resource for the security researcher because the work is really done for you. You can go to that group and get great lists of all sorts of malicious sites. And now I hear that Google is releasing more information on their lists of malicious sites that they've identified and that they block through their search technology. And so we're always happy to see some more information sharing from other organizations helping to identify the bad guys. So what we found is that, talking mostly about the MySpace run, is that there's lots of obfuscation out there. But most of it was essentially benign. Adware, ad syndication, cookies, hit trackers, Google Analytics. These are all sorts of things that use dynamic scripting. They were all over the MySpace pages we spidered. And but in a sense, they're really benign. They weren't actually trying to exploit your browser. They were more trying to make sure that you had to consume their advertisements. So MySpace, at least based on our result, they run a fairly clean ship. In our 400 or 500 JavaScripts, we did not identify any as being clearly malicious. They were obfuscated, they were evasive, but mostly for functionality such as displaying advertisements or tracking your path through various commercial websites. So how do you use this information to identify or to classify good and bad JavaScripts? So our approach, as Daniel showed you, basically we instrumented the SpiderMonkey interpreter. We wrapped and logged a lot of key functions such as object instantiation, string concatenation, uses of escape and unescape, uses of character functions, things of that nature. So with these logs, basically we could generate statistics about the usage and essentially the execution profile of these JavaScripts. How many strings were created during execution? How many objects were instantiated by name? How many document write calls were made? Those kind of things. So we really started looking at trying to fingerprint what kind of ratios or relations between those function calls or those behaviors would indicate a script that's trying to do something bad or untoward, or versus something that is essentially benign but may be trying to obscure its purpose. So this first graph, I apologize if it's hard to make out the titles here. Basically, these are 4 samples, Monkey Chow 1 through 4. And these are 4 samples of malicious JavaScript. And what you're looking at is basically at the very bottom is number of calls to document.write. The next stack above that in the reddish maroon color is basically string instantiations. And because string instantiations are so frequent, we really had to scale those by a factor of 50 to yield graphs that really show anything. You've got calls to eval, you've got element instances, you've got, and at the very top of the stack is object instantiations. So what we're seeing is that string instantiations are very frequent in these malicious JavaScripts. They're creating new strings all over the place. And we believe that's partly a reflection of the use of the string splitting technique we showed earlier, and that the authors of these scripts are being evasive about the actual string content within their scripts. They're adding these strings or encoding them together and creating string instantiations. And also point out that one reason we have so many string instantiations is the plus operator really instantiates 2 objects. Any Java programmers out there will tell you that's the downfall of using string concatenation. So we're seeing a lot of these string instantiations.
I had a question over here before we.
Are you using static counting? You're counting like the number of document writes in the document?
This is as it gets evaluated. So it's not just going through and counting the text. It's actually, it's going to output 1 document write for each time in that loop that it's actually called.
The question was, are we just simply counting the seeing document.write in the syntax of the script? And the answer is no, we instrumented the interpreter so that, for his example was, if you have a loop and you're calling document.write, well, we'd see 50 document writes if that loop went through 50 times. Whereas if you're simply inspecting the syntax of the script and without understanding that it's in some sort of loop structure, you would see, yes, the string document.write appeared once in this script. So just to make the point, we're wrapping and logging a lot of the internals of the interpreter here with the idea of that's a good place to insert yourself if you're really trying to look at the behavior of the script instead of the syntax or the semantics of it. So we're going to look at samples from MySpace, the run. And along the bottom, we've broken it down by domain, host.top-level domain. And as expected, when we spidered, starting at the MySpace homepage, the top domain for number of unique JavaScript documents collected was the myspace.com domain. There's a few interesting things that showed up in there. Photofile.ru is the 5th down. So clearly there's a lot of Russian photo hosting going on MySpace. And then interesting to round out the top 10, there was a tie, so really we had 9, is HillaryClinton.com, which was apparently lots of links to that site through MySpace, and there's a good there's several JavaScripts that are hosted there that you will find if you spider MySpace. So to point out, obviously the number of document writes are a lot higher in proportion with these benign samples in terms of in relation to the other function calls. In the next graph, we're really going to put them side by side. And so the 4 samples on your left are known bad JavaScripts that we identified. The other samples are the collections from MySpace. And what we're seeing as a trend is string instantiation is relatively more common in malicious JavaScripts than it is in benign ones. Also, what we see is that document write calls are relatively more frequent in a benign JavaScript than they are in a known malicious JavaScript. So to speculate on why that might be, a lot of these commercial or benign JavaScripts, they offer a lot of functionality. They're writing out elements to part of the page. They're writing out various HTML content. And so you'll see document write called throughout the script in various functions. However, in the malicious case, typically the author of the script will build up his payload using string instantiations, and then eventually do a lot of times just a single document write of a variable containing their payload, whatever it is, be it shellcode or one of the month of browser bug kind of exploits. And so just really visually, you can see there's really something different here. And then another interesting point is that object instantiation is relatively more popular in the malicious scripts. So what we're seeing, for whatever reason, they're creating more objects. They're instantiating a whole lot more strings, yet they're not calling document write nearly as frequently. And just to go back to this other one, you could see those ratios hold pretty well. You could, the bar graphs are broken by the magnitude of those different values. And so there is definitely a visual pattern there.
So the future of Caffeine Monkey. We're not saying we found an end-all, be-all, placebo solution to internet security, and nobody has that. But we found that we do provide a lot of visual and statistical analysis of what makes a malicious JavaScript or malicious or benign versus benign JavaScript, along with multiple other things that you see throughout your statistical analysis. You can just say what calls are being used most in the wild, things of that nature. So we're releasing this week. It's going to be released on the SecureWorks Research Tools page. It should be out tomorrow sometime, posted up. It's already on its way. So, do everybody a favor, expand on it a little bit, save everybody some time. There's a ton of analysts out there who are doing this JavaScript deobfuscation by hand or as part of an incident response. And this is going to help everybody out in the long run and make us be able to concentrate further down the line and get to securing these web apps. So there's lots of different ways that this could be used. It could be included in a proxy potentially, in some sort of IPS, IDS device, some sort of fuzzy logic, heuristics, in addition to a signature-based approach. Because as we've seen, signature-based approaches, if that's all you're doing, you're going to fail because there's so many different ways in JavaScript. I mean, it's a full programming language, and you can express things in any way, any number of ways. Also, possibility of a Firefox plugin if somebody wanted to get really creative, of having a sandbox JavaScript environment to run things in before it actually got passed up to the JavaScript interpreter within Firefox itself. So that kind of concludes our talk. I wanted to finish up a little early because there's a lot of reception activity happening out there. But we want to have plenty of time for Q&A. I know and
we've got one to start with right here.
Well,
and then they run their obfuscated code for something else that makes it look
right.
like banana job.
Right. So the question.
That's a good point.
The question is, what happens when the attackers start modeling their JavaScript to look the same as the benign stuff? Well, It happens. It's an arms race. But as we've seen time and time again, attackers don't tend to change their attack pattern until it's not working anymore. So as soon as something like this gets really implemented and out there a lot, then you can solve the problem, or at least make it a lot less common. But if nothing ever changes, then it's just going to be the same old, same old.
And you're exactly right that when we're discussing on our team the results, someone said, well, if these results were published, or if this kind of protection technology based on these ratios or the relative frequency of calls was actually widely deployed and was affecting the yield of these attacks, well, then as an author, wouldn't you try to write your JavaScript so its footprint or its fingerprint look just like the ad syndicators or just like Google Analytics? So yes, this has a potential for arms race, and the potential also could be that if this was affecting the author's ability to exploit your machines, they may start coding the scripts to match fingerprints of benign stuff. So that could impact the effectiveness of this approach in the longer term. You're right.
I'm sorry? Well, we haven't exactly developed a full algorithm to definitely show, or this is malicious or this is benign. We've got some good ideas. We haven't fully fleshed out a function that you can just pass things into and say, is it good or bad? But you can visually see. When you look through the logs, you can definitely see, because you're tied in at that debugger level and seeing what's actually done. So right now, there's still a little human heavy on the analysis, but it saves a lot of time just running it through, and then you can look at it that way.
We'll get the green shirt and then you next.
Does Caffeine Monkey offer any sort of an event monitoring system? Like if you're analyzing what's coming through JavaScript, can you define, let's say, I want to keep an eye on things that are going to start requesting resources from alternative sites that we're going to be looking at? The idea being is, let's say I want to build a Firefox plugin that helps me populate ad block. So I wanted to keep looking for things that are going to pull resources off of foobar.com when I'm actually visiting Google now. And it can pop up a little message that says it's going to request information from such a site. Can Caffeine Monkey tell me of such an event so that I can say, okay, fine, that domain, throw it in ad block, don't send any more information? Is it an intercept?
So the idea being kind of detection of the same origin policy or violations of that, where you're getting code from one domain and it's pulling resources off other domains. The tool doesn't do that now, but I think that's definitely would be a good idea to extend it. Basically, you could look, since we've hooked all the critical functions in there, you could look at the arguments and you could break down the URL perhaps and look at, okay, well, I'm at this domain, it's requesting from something in another domain, but that's not built in at the moment. Now, you raised the question about an event model, and that's definitely something on our radar screen to build into the tool. We made the decision, basically on time and resource constraints, not to hook all the on-event handlers. We know that's something we want to do, but basically in the time constraints, that kind of functionality is not in the engine at present.
Brown shirt?
Okay, so this is just following up to Billy's question here. I understand that you don't have full algorithm, that's not the product, so you're not saying that something is definitely malicious versus definitely good. But if you were to take your own libraries, put all your own malicious JavaScript scripts, and use your algorithm on that, and then use the same algorithm on a known clean set, what kind of percentage are you getting with X percent of assuredness?
And right. So the question is really, have we validated this against different corpuses of data? What kind of false positive, false negative are we talking about? At this point, the research is pretty in a fairly early stage in that we're just developing kind of the heuristics, and we're kind of discovering some of the characteristics of these two things. So no, I don't have any good hard numbers for you on that. At present, this technology is not deployed inline in the field. It's not blocking stuff, but that's definitely on the roadmap for how we want to continue this research. But I don't have strong false positive numbers for you right now.
Yeah, without
We can
having-
make the data available. However, with the tool release, we're going to be making the graph data, the MySpace data available. And if you send us email, we could definitely drop you a database dump of what we're working with. So
to follow along on that, we don't have hard numbers. We haven't dropped it into like a statistical analysis program to say like known clean versus known malicious and seeing what the ratios there after we feed in other stuff after it's learned or anything like that. But just on the human analysis level, you can really tell, like easily as an individual looking at it, but programmatically, no. A black shirt again.
Why did you decide to make the solution open source? Because this way you help bad guys to get some information how your mechanism works and to improve their obfuscation
right.
techniques.
Well,
What is the reason of making it open source?
it's a good question. So basically the question was, by releasing this code and by publishing these results, are we just not helping the attackers to increase their game? Well, typically you're not going to be given a tool talk at Black Hat unless you're willing to open source it. But we figured, like many security tools, it's a double-edged sword. A lot of the tools out there, have good uses and bad uses, and this could be a case of one. I mean, I could imagine the scenario where a malicious JavaScript author uses this tool to look at the fingerprints of his work and to make sure, okay, this is clean enough, this is going to bypass security mechanisms. I don't have a real good answer. We feel that this was something that should be released into the community for others to enhance on it, to build on it, and maybe the other scenarios, Firefox plugins, IDS proxies, heuristic devices. But we felt that it was the right thing to do, basically, to open source it. And just like many tools, there's really dual uses for it. Blue?
You said before safe and lightweight, like it's lightweight, but what are the main aspects that make Caffeine Monkey safer than executing it in the JavaScript view? If you send a request, what's to prevent someone from exploiting vulnerabilities in SpiderMonkey or such to attack the tool, or if it was to be built in on ideas like this?
So the question is, why is it safe? What's to keep people from exploiting SpiderMonkey itself? Well, there might be vulnerabilities in there, but as we said, the SpiderMonkey code base that we built on is very mature and it's been around for a long time. And vulnerabilities in JavaScript engines themselves are becoming less and less common as they're very deep down. That said, the tool could have some vulnerabilities. Anyone's foolish to say their product doesn't have vulnerabilities in it. It's the nature of the beast.
And in the current usage of it is essentially a post-processing step. So we would crawl a target, we would index all the information into a database, and then we'd run post-processing analysis where we would feed the scripts into Caffeine Monkey. Caffeine Monkey stores the results into some various database tables. And so it's not quite as interactive as a VM with a browser requesting a page from the web and executing it. So we think that in that post-processing model, it's probably safer. You could run the process that is analyzing these as least privilege. It doesn't have to have any network access other than to the database which stores the samples.
And you wouldn't necessarily need to have access to that. You could download the samples, and then SpiderMonkey itself doesn't have a network stack. But if you're running it all at the same time in a combined tool, then it's feasible that it could go up like that. But as it stands, SpiderMonkey has no network access. Orange shirt?
So just to play devil's advocate, if it was to encounter wild true, what would happen?
Well, it looped. It's a JavaScript interpreter. The question was, what happens if it comes across a while one, while true, something like that. And as it actually is interpreting the JavaScript, it would loop. However, I believe, and don't quote me on this, is that there's things in the JavaScript compilers to detect that and error out before it gets to the interpretation of the bytecode phase.
But Right.
That's right.
So he mentioned in the SpiderMonkey code they've got something defined as a max recursion depth or max branch. So it may detect, that it gets in this condition and exits out under some error condition. But in a naive case, if that wasn't there, yeah, our tool would spin off just like your browser would.
Dark shirt and then light shirt, and I think that's all.
You said that you were getting a list of scripts to test with your tool by looking at your MIME type. Do you have any idea what percentage of the scripts out there on web pages are actually served as a .js with MIME type of JavaScript, as opposed to embedded within a web page or just served with a different MIME type?
The question is, MIME types are how we determine our JavaScript mostly. And so what are we going to do about that, or how do we find it? What are the ratios of that? I'm not sure about the exact ratios. It was an easy way to pull down and get a lot of data quickly, and there are a lot of things that do it that way.
I mean, we could presumably do some post-processing where we look at text HTML documents, we try to parse out script tags, things of that nature, and we're aware that is a weakness, that we're only looking at samples that were identified either as, I think, application X-JavaScript and text/JavaScript. But as you know, you can throw some script tags in your HTML document and it'll be executed. So that's another thing we like to add, is basically doing some post-processing on the various HTML or text or XML documents that we pull back, looking for scripts within those, and then storing them off for analysis.
Even that can get tricky because you could have pages that will execute script without having a script.
Yep.
Right. Yeah, it's the
So a lot of the MySpace
Right.
stuff that gets bought is just because
Right.
there's no script tag in there, but it's just an event handler or something that allows it to run.
Yeah, we didn't tackle that because we were trying to focus more in on getting some results and the core of the research to how to fingerprint these things. And we didn't really want to bite off that problem, as it can be pretty challenging. Right here?
Yeah, I have several comments. First is for that gentleman's question about open source. So my comment is, it doesn't matter whether you publish this open source or commercial software, because bad guys can pay for that, and as if they buy commercial antivirus software to test against malware. They are much richer than we are. So my second comment is, if you make advantage of Opera browser, maybe this task can be accomplished easier, because you can use Windows or Opera or add dependencies before scripts. So you don't need to pay attention to what kind of MIME type it is used.
Okay.
While the script and the browser is feeding the script engine, you get a first chance to insert that.
Right.
All right.
And you don't need to pay attention to eval, because it will trigger another bit.
Right. So I guess the first point is that even if this was a commercial software project, the bad guys would go buy it if it was of value to them. They have money. Obviously, nowadays it's done for profit, and they will have the resources to purchase this if they so chose. And that's exactly right. I really wasn't that. Your second comment was about Opera, and it has a hook or has an object within Opera that we could hook possibly and detect those embedded scripts. Honestly, I'm not that familiar with the internals of Opera, but that sounds like something promising. I could almost imagine using Opera as a tool to pull out the scripts from the content and analyze them further. Thanks.
And over here?
One of the talks earlier today talked about using JavaScript to set up a heap spray, set up for an exploit. Have you considered looking at heuristics to find that kind of thing?
So the question is, have we looked at heuristics to detect heap spray activity? And the answer is not exactly. It's included in the malicious traffic that we've analyzed. Those 4 examples, I'm not sure if any of those included it, but there's various other malicious scripts. And some of them have had it, some of them have not. But we haven't exclusively focused on the heap spray techniques. Though that is a growing concern and used quite a bit these days.
I mean, almost intuitively, it might be easier to detect that kind of attack because it seems to be very noisy. I mean, in a sense, very noisy. So yeah, that may be some low-hanging fruit in terms of detecting that sort of thing versus, you know, a downloader, which might look more similar to an ad syndication or something. Good idea.
All right. I think we're going to wrap it up.
do
If you
one.
have any more questions, y'all
Yeah,
can just come
come.
up to the front, and we're more than happy to talk to you. Thank y'all very much.
Thank you.